All right, well, welcome back, everyone. So the next talk is going to be by Gharibian, and it's going to be a dequantization talk, dequantizing the quantum singular value transform, hardness and applications to quantum chemistry and the quantum PCP conjecture. There's a lot going on in this title, and I'm actually super excited to find out what it all means.
Great. Thanks so much for the introduction, Scott. You were the first person to actually read out the full title when presenting the talk, so I'm very proud of you. I wish I had a prize. Okay, good. So thanks very much also for the introduction, for the invitation to Umesh. So this is going to be joint work with François Legal. This is essentially an extended version of the QIP talk, basically. So we'll go into more details, and I'll be able to tell you a little bit more about proofs and things like this. So let's begin. By the way, really naive question. So this is a Lattices quantum workshop. So do the Lattice people know anything about quantum? Can I assume this? Is that fair? Okay. If there's anything you need to know along the way, you just let me know. Okay, just stop and I'll write stuff on the board. Okay, good. So the theme of this work is really closely related to some of the things we saw this morning related to quantum advantage, right? Which is, where is the boundary between the power of these two models of computing, right? Classical and quantum. And of course, this is one of the driving questions of our field, at least from the CS side. And it's a very broad question. So, in this talk, we're going to sharpen this into 3 guiding questions. Okay. So what exactly do we mean by boundaries? Okay, so the first thing we care about is we want to do things rigorously, right? As Greg was saying, we're kind of like half mathematicians at the very least, like greater than or equal to, right? So we'd like to do things rigorously. And nowadays, we actually have really good frameworks for doing this, right? Over the last few years, there have been these really nice quantum advantage frameworks, which try and make classical computers look bad and quantum computers look good. And then on the flip side, there's been this really nice counter view of dequantization, basically, which tries to make classical algorithms look good and things like quantum machine learning look bad. Okay. So that's one thing we'll touch on. The next thing, of course, we care about is, how can we define a practically meaningfully such boundary, right? So of course, in the long term, we'd probably do something like run Shor's algorithm, right? But of course, in the shorter term, in this NISQ era, right, is there a task that would be actually practically meaningful and useful? Okay, and Scott already touched on a lot of these things, and we're going to be going in the direction of quantum chemistry here, of course. And there has been a very nice Simon's colloquium by Garnet Chan on this topic. So I'll mention a little bit of that later as well. Okay. And finally, of course, anytime we have any sort of boundary between the power of classical and quantum computation, you could always ask, what does it say about the physics of the underlying models, right? So for example, there's this very infamous quantum PCP conjecture, right, which has resisted efforts for years. And one way to interpret this conjecture, if it holds, is to say that natural quantum systems can be exponentially complex, even at high temperature. Okay, so in this work, basically, we take these 3 guiding questions and we intertwine them into one narrative. That's the goal. And so on this slide here, I'm going to outline kind of the main points of this work, basically at an informal level. Okay, so we're talking about boundaries between the power of classical and quantum computing. So the first thing I need to do is, I need to define the boundary, right? So what's the boundary? The boundary is going to be a practical computational problem, which I'll call GLH. It's taken right out of quantum chemistry, okay? And what you need to know about this problem at this point is that, for quantum chemistry applications, right, the precision to which you need to solve this problem is inverse polynomial in the length of your system. Okay, so that's kind of the gold standard you're going for. Here we're assuming the Hamiltonian has been renormalized. Okay, so first we'll formalize this problem. The next thing we'll do is we'll show that if you're willing to give up some of this precision, right? You're not going to solve this thing to really good precision, but only to this sloppy 1 over constant precision, right? Then you can actually solve this problem efficiently classically if you get to add to your computational model these so-called sampling assumptions, which nowadays are more or less becoming standard in our field. And this is where we're going to see this dequantization of the quantum singular value transform in a particular setting, in the setting of sparse matrices and constant precision. So that's a positive result. And then on the flip side, again, we want this boundary between classical and quantum. So this is the classical side of it. The quantum side of it is that if we go back to this 1 over poly precision that chemists really care about, then this problem is actually BQP hard to solve in the worst case. Okay. And I'll say more about what this means for quantum advantage briefly later. Okay. And finally, what does all of this say about the quantum PCP conjecture? Good. So any questions before we begin? That's where we're going. Again, feel free to stop me at any time. Good. So let's start by defining this problem GLH. So for those of you familiar with Hamiltonian complexity, you can probably guess that the LH in GLH stands for the local Hamiltonian problem. Okay. And so what is this problem? In this problem, I'm giving you a local Hamiltonian H on n qubits. Okay. And your goal is to estimate the ground state energy of this Hamiltonian. Okay, the smallest eigenvalue here it is, this lambda min. Okay, and is the smallest eigenvalue at most some alpha, or is it at least some beta? And the point here is that there's some promise, of course. Alpha and beta are not too close together. Okay, so they need to be at least 1/poly separated. Okay, so this is kind of the canonical QMA complete problem in quantum complexity theory. We've known that for like 20 years now. And we know many hardness results in all sorts of geometries and for various physically motivated models. Okay, good. Let me briefly touch on this because we're going to come back to the QPCP conjecture later. So here I said it's very important that the promise gap is 1/poly. And you might ask, what if we're going to be sloppy here and ask for a constant promise gap? And when you do that, then you fall into this regime of the so-called quantum PCP conjecture. Okay, and here it's conjectured that this problem remains QMA complete, even if you're sloppy. You only estimate this ground state energy to constant precision. Of course, what we do know already is that this problem certainly at least can be hard, because you can embed classical CSPs into this framework, okay, in this constant precision setting. Okay, any questions about the slide? Because if you don't understand the slide, the rest of the talk will make no sense. Is it safe to assume everybody knows what a Hamiltonian is? Let me know if not. Good. Okay, good. So this is the local Hamiltonian problem, right? And we've been studying this from a theoretical perspective for 2 decades now. And while we think we're important people doing this, in the actual real world, right? This is supposed to be us in theory land, like sitting on the moon, and we're off staring into what people are doing in the real world. Chemists are trying to actually solve this problem in practice. Okay. Okay, and so what do they actually try and do, right, to solve this problem? Well, I mean, first, let me refer you to this really nice Simon's colloquium on April 12th. So this was a really nice talk by Garnet Chen. It was a little bit deflating, perhaps, right? I mean, it was an honest talk, but it's a bit deflating about our prospects here, at least to date. But this is essentially what they do. Okay, the first things they do is that they want to solve for these ground state energies in quantum chemistry. Okay, that's a very important task. And so what they do is they first use a classical heuristic, okay, to try and compute a good approximating ground state. Okay, it's not necessarily the ground state, but it's going to be some guiding state. Okay. Now, I want to be really, really clear. Number one, that first of all, there's no guarantee that a good classically representable such approximate ground state should even exist in the first place. That's not clear at all, right? And these are not polytime algorithms, right? They're heuristics. So let me be really, really clear. So in some cases, in practice, I mean, it turns out that some of these heuristics work really, really well, right? So here's there are some examples, but in general, you're not guaranteed that they're going to work. And this is really one of the things that Garnet really touched on in his talk here. Okay. Good. So what do you do once you have this guiding state in your at your disposal, right? Well, if I have a quantum computer at my disposal, right, I have an approximation to my ground state, and I just want to solve an eigenvalue problem, right? So what am I going to do? The obvious thing, right? I'm going to run phase estimation, right? That's what we always do. Okay. And more recently, there are these variational approaches. Again, this is what Garnet was really talking about, but it all fits into the same boat. Okay, and in this talk, I'm not going to talk about these variational approaches. I'm just talking about QPE. Okay, we won't really talk about QPE directly either, of course. Okay, so this is essentially what we want to formalize as the GLH problem. So let me do that. So this is the so-called guided local Hamiltonian problem. Okay, this is the same definition as before as for the local Hamiltonian problem. What's new are these lines in red. Okay, so in addition to the Hamiltonian, I'm also giving you some representation of a guiding state psi, okay, and a promise that this state has some good overlap, some delta overlap with the ground space. Okay, yeah, question.
for when they're out? Is it-
Yeah, I'm assuming that it's for both yes and no instances. You always get a guiding state.
Oh, that's close to the ground state.
Yeah, has some delta overlap.
Okay.
And that's what makes the reduction non-trivial. I mean, it's not hard to be honest, but it's also non-trivial for that reason. Yeah.
So the Hartree block from the previous slide, you said they got 99% of the energy.
That's what the physicists wrote in their paper, yes.
But that's different to what you have here, right?
That can be quite different. That's right. So you can use, if you're very careful, that's a very good point. So for example, it's known that on dense constraint satisfaction systems, product states are really good approximations to get you the right energy, but they're not actually good approximations to the ground state itself, right? So some local observables can be approximate well with that ansatz, but not others, right? So that's not the same as this, right? This is a stronger promise in some sense. Absolutely.
So is the sampling assumption going to be something like that you can sample from the output distribution of psi?
Yes.
Oh, okay, good,
Exactly.
good. I was wondering what that could mean in this context.
Yeah, I'll define it. Yeah. It's
All right,
good.
thanks.
Okay, so this is actually this distinction between the close energy versus the
That's right.
having overlap. This one can tease it apart a little bit more because practice where this is not necessarily close energy, not necessarily large overlap at ground state, but getting states for which local observables or
That's right. That's typically what you. That's right.
that's where they're trying to get to. So what would they say to this? Is this too strong for characteristics, and so they don't really have a guiding thing? What's the how do you?
That's a good question. I'm not sure the answer to that question, right? But you're absolutely right, right? I mean, typically you just want to reproduce some local observables, right? That's the goal.
So what's the reason that you take this condition as a promise?
Well, it was one way to formalize it, right? It's certainly one way to formalize it, right? And presumably there are other good ways as well, right? But when you take on this definition, then you can prove these certain positive negative results. But on the flip side, it also makes it harder to find that bloody thing, right?
But that's harder to prove something.
That's right.
It's harder to prove something with an energy condition. With an energy promise.
This
on the
is a
ground.
stronger condition.
Yeah, this is a stronger condition. Absolutely. Yeah, I agree. Good.
Sorry, just another question. You would be perfectly, I'm assuming you'd be perfectly fine if the projection on the low energy subspace is large instead of ground space.
Oh yeah. I mean, you might need a spectral gap then, right? Like if you want to use phase estimation to solve this, I mean,
No, I mean, well, but the fact that you have alpha and beta, right? So you already have a promise gap.
oh yeah, then in that case, yeah. So sorry, I'm just thinking more in the actual practice setting where you don't have a promise gap. Yeah.
Already know the K plus 5. So is that right? So QMA complete for K plus 5. And then what, so is it just the K plus like 4 and 3
Okay, so
cases or what?
this is the original result showing essentially quantum completeness for this problem.
Yes.
And now we know all sorts of things, like even if you put these things on a line, and they're even translation invariant, you can get hardness results in there. That has nothing to do with the PCB setting though, right? That's in the 1 over Pauli precision setting. The only results we know in the constant precision setting are just if you embed classical hamiltonians, like diagonal ones, basically. Does that answer your question?
Yeah, you have two different assumptions. Okay.
Any others?
How should we think of delta?
I'm sorry?
How should we think of delta in the guidance here?
How should we think of that? Oh yeah, okay. So for our results, I mean, we can show that the problem will be deeply hard even if I give you a constant delta here. Right, so classical computer, even if I give you really like 3/4 overlap, let's say with the ground state, the classical computer doesn't know what to do with this basically. And I believe for the dequantization, it's also going to be constant. You need all our parameters to be constant for the dequantization to work. So all our results think of delta as a constant. Okay, yeah, so, we have to be very careful here, right? I mean, I'm saying I'm going to give you some representation of a guiding state, right? So what do I mean by that? Obviously, we can't write this thing down explicitly. And so we're going to use two classes of representations for this work. The first one is the so-called sampling axis representation. Okay, this is obviously going to have to do with this dequantization. And once we take this representation, which I'll define shortly, we'll see that this problem is going to be classically solvable if basically all the parameters are constant. So constant precision, okay, constant overlap with the ground space. Okay, so that's the positive result. And here we say, okay, if we return to that 1 over poly setting we want for solving quantum chemistry problems, the choice of representation we'll use here is something even simpler. It's something called the semi-classical state. And here we'll get BQP hardness. Okay.
Wait, I mean, these conditions don't even seem mutually exclusive.
They're not. If you have, I'll define what this is, but once you have this, you could certainly implement this.
Oh, okay. So the issue is about the representation.
Yeah.
Because otherwise you would have just proved that P equals BQP.
No. The representation.
All right.
I mean, this representation is not so useful explicitly for a classical algorithm, generally speaking. We want to give it some sort of sample.
All right. Fine. So it's fine. So the two things involve, the two results involve different representations of the state. And what about like if alpha and beta are like, and delta are like 1 over log? Like what's going to happen there?
Oh, you'll get the dequantization, I think, should end up running a quasi-poly as opposed to polyton. Like you'll see the.
So it's so basically these like 1 over these parameters is going to show up in an exponent.
Essentially, yeah. So it's going to be like the sparsity of your matrix to the degree of the polynomial you need to choose, and that has to do with this.
All right.
Good. So this is the problem GLH. We're going to study this for the rest of the talk. But before I do that, let me just try and tell you kind of what's the punchline at this point. Okay. And how does this tie into this whole quantum advantage that was talked about this morning? So we can show that this problem to within that 1 over poly precision is BQP hard. It's also in BQP because you just run phase estimation, given a good guiding state. And so this problem GLH, or the 1 over poly precision, perfectly characterizes what it means to do efficient quantum computation. And so the obvious question you want to ask yourself then is that is this a practically meaningful task to experimentally demonstrate something like quantum advantage? Okay. Now we have to be very careful about this, right? I've got this red question mark here, and the results we have here are worst case results. So here, when I say BQP hard, this is not an average case reduction, it's a worst case reduction, right? And so we're nowhere near kind of the bar of hardness you really want for these quantum advantage results, right? Typically, you want to have average case hardness also in the noisy setting.
Well, I mean, once something is BQP hard, then you could just combine it with any like hard on average instance of a BQP problem, right? And to run the reduction. And that'll give you some distribution over instances, right? Maybe not natural for your problem.
Yeah, okay.
By the way, what does the boxing hamburger represent?
So because everything's being recorded nowadays, I've been more careful about sourcing my pictures.
Oh.
And so there's a free sourceware. And the only thing that came up when I wrote punchline is this bloody thing. So it ended up on the slide.
Okay.
You're also the first person to ask me this question.
Is it this?
Well, that's the question, right? So here you're crossing your fingers and hoping these variational algorithms will do their trick. But as Garnett's talk gave away, that doesn't necessarily seem to be the case. And maybe I should make one point really clear here, right? To do this, right, there are two parts to this, right? There's getting your hands on that guiding state, the classical heuristics, and then there's the actual quantum side of it, which is estimating the energy, right? So Garnett's talk was basically saying that the first part of this, getting a good guiding state, seems very hard. That's what I took away from this talk. And I mean, if you could build a large-scale quantum computer, then you could certainly do the phase estimation. But I don't know too much about the variational algorithms, to be honest. What you can expect out of those in terms of estimating the energy. Yeah, assuming you had a good guiding state, because I don't. So really here, this is a big question mark. This is not like something that, okay, we should obviously do this, but it's a question.
What precision scaling is important for practical applications. I mean, for
Well, so normally what you want is you want like there's some constant precision you want in the quantum chemistry, like that's gold standard. I forget what the units worth is, like I'm not a chemist, right? But what we do in this work is we renormalize the Hamiltonian so that it has a constant norm, and therefore then you're looking at a 1/r Pauli precision, okay, with the system size, right? Whereas normally in chemistry they don't need to renormalize; they just want constant irrespective of the length of the system. So that's why we have 1/r Pauli.
So I'm only behind. So when you say sampling access, you
I haven't defined it yet. Okay, let me define it because I think I'm quite behind schedule. So let me get to that. Okay, this is what I was just saying. This is worst case complexity. I'll bug you more about what you were saying after. In the interest of time, let me just go. Okay, good. So for the hardness result, all right, I need to tell you what is this representation of the state psi. What is a semi-classical state? And so this is a really, really simple classical state. There's nothing fancy here. Basically, it's a special case of what Alex Rillo and co-authors call subset states. Okay, and all it is basically you pick a subset S of strings and you give me the equal superposition over those. Okay. What's different in our setting versus Grillo and all is that our subset is poly-size, and so this ensures that the state psi has a really simple classical distribution. And so what we can show here basically is that even if you give me essentially constant overlap with the ground space, okay, if you want this precision, then this problem is solved. You need to simulate a quantum computer. So I think I'm until 3:30. Is that right?
Yeah.
Good. So I'll cut out as I go to make things fit. Okay, so the perm sketch, basically, how do we make this work? This is not a difficult thing to prove, to be clear. There is a little bit of trickery that's needed, however. What you want to do is you want to take an arbitrary BQT computation, right? And you want to map it to an instance of GLH, basically, so that you have two things here, right? Number one is, this is kind of the usual one out of this, right? So if you accept its input, then the ground state energy is small. If you reject, ground state energy is large. That's very easy to get. Okay, that's this point. We just plug in Feynman's Minkowski circuit Hamiltonian construction. What's a bit trickier to get is that we have to design this guiding state. Okay, both the yes and the no cases. And so this is where we have to do a bit more work in the reduction. Okay. So let me tell you a little bit about how this goes. To tell you a bit about how this goes, well, okay, why don't I just go to the sampling part, and then if I have time, I'll come back to this. Is anybody going to be very upset with me if I do that? So the trick, of course, is that in the no case, it's hard to design well, not hard, but it's not immediately trivial how to design the guiding state. And there are various ways you can get around this, basically. And so we use some trickery from Anders and Binus, but if there's time, I'll come back to this later. Let's put it that way. I'd rather you guys take the time to ask me questions. Good. So let me tell you about the dequantization aspect then. Make sure we cover this. Okay. So in this result, basically, we're going to give you a sampleable state. And what do I mean by that? So there's this big nasty definition on the slide. Just ignore this zeta parameter. Zeta is kind of a noise parameter for us. And it basically says that, okay, you can tolerate some error, some noise zeta in your sampling. Okay, but imagine a perfect sampling. So zeta is 0. And so really just focus on these two. Okay, what does it mean to have sampling access to some gigantic state psi? It means two things. Okay, number one, you give me an index, right? And I assume there's some efficient way to compute the amplitude psi I in poly time. Okay, so it's just the usual query access model. And this alone to a classical computer is pretty useless, right? I mean, there's a giant vector, right? I have poly time, where am I supposed to look in this vector? I have no idea. And that's where the sampling access comes in, right? This basically says that I can figure out what are the heaviest elements in my vector in some sense. Okay, so I can sample from a distribution P, right? And this distribution, what it does is it returns an index into your vector. And that index, the odds of seeing that index really just scale with the norm squared of that entry. Okay, so the heaviest elements are most likely to get sampled. Okay, so this allows us to zoom in on those heavy elements. So when zeta is 0, this is literally just Tang's definition from her breakthrough work on dequantization. Okay. Questions about this definition?
Does zeta scale with the system size?
I'm sorry?
Does zeta scale with the system size?
The zeta scale with the system size. No, I don't remember. In our work, we can't tolerate all zeta. Like there is some threshold in our work. I don't remember exactly what we got, to be honest with you. But I think you can tolerate certainly constants here, right? And how big the constant got out. Okay, so how do we? So what's the main theorem we show here? Here we show that if all your parameters are constant, basically, then you can solve this problem in Paulian time. Okay. And what's the sketch of the proof? Basically, these are the main components. I won't have time to tell you about all of them, but the basic premise is this. You want to solve an eigenvalue problem, right? So the first thing you do is you reduce it to a singular value problem. I mean, that's kind of natural. You would expect that to happen. Okay, and of course, this is also in the guided setting. Okay, and so also constant precision. And once you have this, this is where you do this dequantization trick, basically. And here we show that you can dequantize the so-called sparse quantum singular value transform, again, in the constant precision setting. Okay, and then to kind of plug this back in here, we will have to process our Hamiltonian with some polynomial p. And what's really important here is that because I'm only worried about solving it in the constant precision setting, then this polynomial can be constant degree. Okay, and this degree is what's going to show up in the runtime. This is back to your question. Okay, so let me tell you about this step of the proof. Okay, so for this, let me define what I mean by quantum, well, just singular value transform for this discussion. Okay, so this is a pretty nasty definition, but I'm just going to ask you to focus here, basically. Okay, so what are we given as input? We've got a matrix A, which is sparse, S sparse. Okay, and we're given a polynomial P, which is even. And then let's just imagine for now we've got two vectors V and U, to which we get sampling access. Okay, and your goal is to do this. Basically, take the singular value transformation of A, or decomposition of A, and then apply this polynomial to the singular values. You can think of it that way. Okay, and once you do that, I need to output a scalar. So then you take the inner product with these two vectors to which are given as part of the input, to which we assume we have sampling access. Okay, and your job is to estimate this quantity to some additive error, epsilon. For us, epsilon is constant. Okay, you'll notice there's absolutely nothing quantum about this, right? The quantum singular value transform algorithm, what it does is it basically produces this state, right? I mean, given this a state U, it produces this product. Okay, so in that sense, this will dequantize that algorithm. In this setting, not in all settings, of course, right? Let me be clear. Okay, so here's the zeta we tolerate. Back to your question, right? For us, epsilon is constant, so at most 1/8 is what we can achieve. Good. This is the runtime. This is Scott's question. There's the degree. Okay. Good. So how do we do this? So the proof is very natural. Okay. It's also very similar to what actually Tang does in her work. Okay. And if you've seen like these earlier works on like randomized linear algebra, this is very similar to what they do. Okay. So here's the idea, right? I'm trying to approximate this thing given sampling access, let's say, to V and U. And so what do I have? Well, I've got an inner product, right? So what's an inner product? Well, I just take, for example, I have a big sum, right? And then I take the ith entry of this vector and the ith entry of this vector, and I multiply them together, and then I add them to my big sum. That's an inner product. And of course, what's difficult here is that these vectors are exponentially long. So since we have this very nice sampling access to V, however, right? I know where the heaviest elements are, right? So I can use that in a random experiment, right? So what I'll do is I'll just pick R random entries out of V using the sampling access and do the following. Okay, so like I said, it's very natural. Repeat this some R times, which just depends on the area you want. Okay, so what I'll do is first, I have sampling access to this. So let me just pull out the jth index on the left-hand side. Okay, and then once I have the index according to its weight, I can compute the corresponding entry Vj. Okay, and on the right-hand side, this is slightly non-trivial. There's a recursive step you have to take here. But the point is that given just query access to U, it turns out that I can compute the jth index of this W. And here, what's really, really important is the fact that A is sparse. Okay, that's very important. And finally, this is just, you add this running total to your average. You've got to do some appropriate rescaling because I'm only taking a very small number of samples out of my entire inner product. And apply the Chebyshev's inequality, and presto, you'll see that you'll be within the error bounds you want with good probability. Okay, so again, it's arguably quite natural. Any questions here? So over here, this tells us how to do this. Okay, we could dequantize this. There is this one other step in between that allows us to go from here to here, basically. Let me tell you just briefly about what this is doing, what this step is for. And it's going to have to do with the fact that I'm going to allow any choice of constants in my input. Okay. So basically, the idea is that you can rather simply modify a polynomial construction from Loewen-Schwang, right, to get a constant degree polynomial that basically does this very nice processing of the singular values of the matrix for you. Okay, so basically what it's going to do is I'm looking for, I'm being given a range A to B. Is there a singular value in that range? Okay. And what this thing will do is that when you process these singular values with this polynomial, it'll kind of tear apart the singular values. So everything in this range gets mapped approximately to 1. Okay. And everything that's not in that range gets mapped approximately to 0. Okay, so now it's very easy for me to tell if there was something in this range because, well, now they're quite far apart. And so even if I have a sloppy approximation to my ground state, I could still distinguish whether I'm in this case or this case, essentially, or to my corresponding singular vector, I should say. So once you have that, basically, then you just run that dequantization algorithm on the processed version of your matrix. Okay. Questions? It still works. It's just that the runtime goes to super poly. Right. Over here, there's absolutely nothing wrong with that. And in fact, I was asking Francois about this, like in terms of, so here, if you want 1 over poly precision, then the degree of your polynomial has to grow as well as a polynomial. That's the problem, because I mean, you're trying to resolve like a very small slice of the singular values now. It's like 1 over poly wide, and so this polynomial, you can imagine that it needs to kind of fluctuate quite a lot in some sense. It can't just be some flat thing.
Going back to Scott's question, so yeah. If you have a log, if you define it, the polylog is a problem, right?
Yeah. Okay. Yeah. So then you get a quasi-poly.
But if it's just log, it's a simple log, then it's defined.
Oh, if it's a simple log. Yeah, I suppose that should be fine. Somehow I feel like it shouldn't. I feel like I've had this discussion with Francois over the last month. But okay, at least according to this, it looks like it's fine.
Just to say, like in many physical setup, I mean, the degree does need to increase with respect to n, right? Because your Hamiltonian norm grows with respect to the system size. You want some sort of constant precision, so D should at least be largest in the system size. So you do have an exponential scaling with respect to the degree.
Right, sorry.
I'm just saying that for many physical Hamiltonians, such as the local Hamiltonian, the norm of the Hamiltonian grows with respect to the system size.
That's right.
You want some constant precision.
That's right. Yeah. So here the word no. Okay, sorry. I should clarify this.
Sorry. Not you. Many people want constant precision.
That's right. With respect to this unnormalized.
Yeah.
That's right. That's
right.
And
then this thing really grows.
Sure. Okay. So let me see what this says about quantum PCB basically. Okay. So the quantum PCB conjecture just basically says that this local Hamiltonian problem, when the threshold or the level of precision you want, if it's not 1 over poly, but if it's constant, we believe that this should still be QMA hard. And so what we can show is that once you have this dequantization under your belt, basically it's not very difficult to adapt that to show that exactly in this regime, right, in this quantum PCP regime, if you're promised that there's a good guiding state that has this sampling property, well, then this quantum PCP theorem just can't hold, because you could verify that thing in Merlin Arthur. Okay, so obviously nobody in their right minds, I think, expects this thing to exist in general, to have a good guiding state with this property. And so can you prove that it doesn't exist? Right, and right now we can't. And so we just turn it into a conjecture. Right, and so we'll literally rip off this very nice NLTS conjecture of Friedman and Hastings. And what this really says is that if you believe the quantum PCP conjecture, then there has to be a family of local Hamiltonians, okay, and some constant epsilon, so that basically the low energy space of this Hamiltonian, should not have a nice classical description, okay, which specifically they looked at constant depth quantum circuits. Okay, and so if you just take this definition literally and just copy paste it and just change your representation of the state, you can get what we call the NLSS conjecture. And here we're positing that you obviously should not have a state that has good sampling access. Okay, because otherwise, our result on the previous slide would say that in this constant error regime, the verification of that problem would not be QMA hard, it would fall into MA.
So then would you just get QMA equals MA?
Yes.
I see.
So I guess I have a few minutes left.
Yeah.
Yeah, okay, I can go back to the BGP for a second. I don't want to say too much about it, but it wasn't so bad. So what do I really want to tell you here? So in this BQP hardness proof, we wanted to take a BQP circuit U and embed it into a Hamiltonian for one of these GLH instances, right? And in the S case, whenever you have, I won't go through this in any serious detail, right? But the point is that in the S case, when you do this reduction, right, there is a good guiding state, or there's a good state you can copy at least to design your guiding state, right? And so there's a so-called history state, which embeds basically the behavior view, okay, into a low energy state. And so you can play various kind of standard tricks to make it so that something very simple, essentially the initial state of your computation, is going to be a very good approximation to that history state. Here you play that really stupid trick where I can take my circuit, right? It's got M gates in it. And if I just kind of double the length of that circuit and use identities as the first half of that computation, this idling trick, then essentially I know exactly what half the weight in this history state looks like. It's just a trivial start state. Okay. Good. So that's how you design the S case. The slightly trickier thing is that in the no case, typically we don't have this history state to guide us. Right? So how do you design this guiding state when you don't know what the ground state looks like or the ground space looks like? And so here we use this really cute trick of Anderson minus, and here he was studying something completely different. This is kind of relating back to Umesh's question about estimating local observables. The right complexity class for this turns out to be not QMA, but P to the QMA log. Okay, and so what is this cute little gadget he has? Basically, it allows you to design, the reason why we use this is it lets us design the ground space in the no case. Okay, and how does this work? It's basically here. So essentially, I'm going to have a block diagonal encoding. Okay, so this is the Hamiltonian that comes out of the Kitaev construction when you plug in your circuit U. Okay, and I tag that with a 1. And in the other block, I just put in something trivial about it's the identity, but it's designed so that the energy here is strictly between the two promised parameters. Okay, and so why does this help us? Well, if the ground state energy of the Hamiltonian is small, okay, then for sure, since the minimum eigenvalue here is alpha plus beta over 2, here will be at most alpha. This is smaller now. And so I know the ground space is here. And then I know that in the S case, now I'm in the S case, right? Then I know that I'm in the S case, I'm over here. And so I can simulate that history state. Okay, and so this will be a good guiding state. This here is the history state from the previous slide. And in the null case, when my ground state energy is at least beta for this guy, then the smallest eigenvalue is actually hiding here because this has an eigenvalue smaller than beta. And here, this is a trivial space, right? It's just the identity. Okay, so everything is an eigenvector here. So I can use that exact same psi history state approximation. The only thing is I need to tag it with a 0 rather than a 1 because it's in this block. And that's why you see this plus here. So it's a very simple guiding state. Okay, so that's all I have to say about this. Any last questions? Yeah, go ahead.
Hardness?
Yeah.
It seems that somehow is accused in hardness. This guy is. Can you come your result to specific this problem? No, I don't think so. Because like I think you would need to know the classical proof in advance. For hardness. Yeah. Like how do you do the reduction? Well, how do I get the guiding state, right? Wait. Okay. The guiding state is just the witness, like the witness that you don't know what it is, but the prover can provide it to you. Yeah. That's what everything that you have. But okay, sorry. The guiding state needs to be specified beforehand, right? At the time of the reduction. Okay, the point is, the definition of the problem wouldn't have the guiding state. The guiding state is provided by the prover. But anyway, but how do you then you have to verify the guiding state if it's provided by the prover, right? Whereas here's part of the promise. I mean, I see what you mean. Yeah, I mean, you can imagine the QSMA version where I give you a claimed guiding state, yeah. But then now there's a question: how do you verify this? If it's a substate as you can construct with many elements in this composition, you can construct it. Yeah, that's right. And then do it. Yeah, then you could see if it's good enough to get this alpha beta. That's right. Yeah, in that case. Yeah. So then it would really depend on the representation. Yeah, I did it right.
Other questions?
So the previous dequantization results needs to be low rank. So why is it not here?
Oh, that's a good question. Okay, yeah. So in the previous dequantization results, like that Andras was on, that's in this low rank setting. That's right. So here we get in the sparse setting, and the reason, I mean, the only thing we really need is so the actual dequantization, but the procedure. Where we go? Here, right? Basically, this thing over here, it doesn't, the only property it needs for A, right? It doesn't care about the rank of A, it just cares about the sparsity of A. And intuitively, this is the reason why, right? If A is sparse, okay, let's say it's a poly number of elements per row, right? Then classically, if you have query access to U, then you can figure out what this product is going to be because you only need to look at a poly number of entries in this matrix A. But if it's not sparse and it's low rank, I'm not sure how, like this approach doesn't seem like you'll look at all of that. It seems different. I don't know if I'm just disagree, but to me, it looks very different, right? So in some sense, this is like really simple, right? It's just using the fact that A is mostly zeros, right? And then you can just very explicitly kind of do the inner product yourself, possibly.
I think this is why you actually constant because you assume that the sparse is only polynomial. Sparse is polynomial, that's very possible. That's why I think that there's a require this
I think that sounds right.
because if you consider local hamiltonians or if you don't consider sparse,
oh, that's right. Yeah, that's actually, yeah, absolutely.
Yeah. So, but with this mainstream appealing is no case of this.
Yeah. Yeah, that's right. Yeah. What about it? So, the question I should.
Yeah. So, what is the mainstream? Is that consider this tensor product?
Yeah, basically, I mean, here. what basically I'm just applying this did is like here you have a class where you're making queries to a QMA oracle. So the question is, how do you embed that into like a history state construction? And it turns out the way to do it, or at least one way to do it, is by using this gadget where you kind of have this block diagonal space where intuitively this is encoding the answer to the QMA query. So this is in the yes case, you're in this block, and in no case you're in this block. And so this is a simpler version of his, because in his case he's doing a long number of queries and here we just have one exception.
Hey, anyone else? No. All right, well,
Bobby has something about this guiding state with stochastic hamiltonians. Yeah, I asked Francois about this. I don't think so. I don't think we have any like formal link or anything like this. Yeah, that's right. For these like Markov chain simulation algorithms. Yeah, absolutely. Yeah, that's right. That's what the first thing I thought of, in fact, when we did this. But maybe I'll take a very quick moment to do some just things here. Shameless self-promotion. A number of people asked us for this paper. We talked about it here at 22. It's finally up today. So I'm here this week if you want to talk about this. This is a totally different topic. This is on quantum space complexity and things like quantum sandwiches theorem or unentangled proof systems. So if this kind of thing interests you, you're also welcome to talk to me. Okay, that's it.